Actually, let me first start by telling you that I lied to you last week when we were talking about final exam stuff.
Only like five of us were here, so it didn't really matter.
Okay, good. Let me unlike. Now, I mentioned that maybe we could take it on the last day of classes, but actually I'm confused. That's the week that I'm not here. So I'm not here on the last week of classes. I'm not physically here.
So you gotta do a take home.
It's perfect.
No, so we'll have the exam on. You really don't want to take home. Actually, God, where is it? Not this thing. Not the academic calendar.
So it's earlier?
It is on the 11th. I think this is it. Final exam schedule fall 2017. Oh, God. We meet on Monday, Wednesday at 5 p.m. Which may not be this.
No, you
God.
just had it.
That's Monday at 5, which is not the same as Monday, Wednesday at. And Monday, Wednesday at 6:30. That's my programming class.
Graduates first.
So, MW space 5 doesn't exist. Two spaces? Ha! So,
December 6th.
December 6th, Wednesday, December 6th at 6.
When is the Monday, Wednesday, 6:30?
Sorry?
Nothing.
It's not that bad, right? It's just,
Depends on the test.
well, it'll be easy.
I appreciate
It is hard.
I was about. Can you just out of curiosity, see what Monday, Wednesday, 6:30?
Monday, Wednesday, 6:30 is December 11th.
Okay. So we have a 5-day spread. That's good.
Oh, that's for your other class?
Yeah.
Yeah, Monday, Wednesday, 5 is on Wednesday, December 6th.
No, I like that. I like that. Yeah.
December 6th.
Are you going to give us a sample?
I will try very, very hard. I will give you guys a sample. Politicians promise. Okay, so now we'll figure out, I think what will happen is I'll figure out some way to have somebody record this stuff and then you can come and do the presentations or you can just submit them online.
We won't be able to get to the classroom without you.
We can arrange stuff. We can call the police.
We can just
Should we just make it everybody online and we'll discuss those things, right?
Sounds good.
I'll require you to at least, I hope that you would watch all of them, but I'll require you to at least watch 2 and comment on them. How about that?
Seems fair. Standard procedure.
I mean, expect that you would probably watch all of them, right? And I am assuming that you would record something like what I am doing, as opposed to recording yourselves.
Selfie.
Record your voice and the screen.
okay. That's fair.
But if you prefer to record yourself, that's cool. We'll have the slides, right? So we can go through. Cool.
Does the person with the most viewers get extra credit?
Sorry?
I
Yeah.
You get extra credit.
Everybody watch everybody's.
And if you don't mind, the easiest way to deal with that stuff is to actually post it on YouTube and they'll figure out how to set it up. And then just post the link. But if somebody prefers not to have their stuff on YouTube for whatever reason, that's perfectly okay. So let's talk a little bit about approximation algorithms. And that actually means that we only have this lecture and 2 more, and then the last one is review.
Wow.
And then we have a week off for Thanksgiving, and then that week we are done. Life is fun when you're having flies, as the frog would say. What do you do when you have an NP-complete problem, right? And actually, they're starting to cheat and say NP-hard, right? Because it may be even worse than NP-complete. So, we have 3 options, right? We have 3 things that we cannot have. We can either not solve arbitrary instances of the problem, so it works for certain things, but not all of them. We cannot find the optimal solution. We can find a solution, we can find a good solution, but not necessarily the optimal. We are not guaranteed that it's the optimal. Or we cannot do it in polynomial time. We talked a little bit about some that work for arbitrary instances. This is more about, well, can you find a p-approximation algorithm, right? That's guaranteed to run in polynomial time. It solves arbitrary instances, but doesn't find the optimal. It finds a solution within ratio, that's rho, right, of the true optimal. A really cool thing is that we or they, I couldn't find anything, but they managed to prove that the solution is close to the optimum without being able to find the optimum, because that's what I cannot do, right? So how can I prove that it's close? So they kind of define, well, the optimum has to be like this or like that, and so prove that these things work. And so it is a really cool set of techniques that could allow you to solve NP-complete or NP-hard problems by being close to the optimal, finding good solutions, but not necessarily optimal ones. What's the difference between NP-hard and NP-complete?
All NP complete. I mean, all NP hard. NP complete is within all NP hard.
NP-complete is a subset of NP-hard, yes, but what's the difference? What's the thing that NP-complete have that not all NP-hard have?
Can reduce.
Polynomial space.
The reduction is NP-hard. NP-complete are also in NP, whereas NP-hard may not be in NP, so they may be even worse than NP-complete. So, and we'll see how many algorithms we get to talk about. The load balancing algorithm, you have m identical machines, n jobs. Each job has a processing time, so job J has processing time Tj. Obviously, job J must run continuously on one machine. A machine can process at most one job at a time. So the load of a machine is the sum of the times that it has a job assigned to it. And the make span is the maximum load on any machine. So what we are really trying to do is to balance the load on the machines, right? It also, the make span, what it really, although we try to balance, what it really does is minimize the total time that you have to run. So the maximum load on a machine, that's what you will have to wait to finish all these things. So the load balancing problem is assign each job to a machine to minimize the make span, to minimize the maximum load on a machine. Load balancing is hard, even if you have only 2 machines, because you could make it as finding finding 2 subsets of equal weight, which is an NP-hard problem, the partition problem. So you could just say, well, you have 2 machines, and so if we had an algorithmic, a polynomial solution to this, we would solve partition, and so we would find P equals NP. So it is hard. What can we do, right? Well, there is a greedy algorithm that says, okay, let's take all the jobs and at any given time assign the job to a machine whose load is the smallest. So you kind of go, initially you go round robin and then, oh, which one has less? I'll give it to this one. Does that make sense? Is it optimal? No, right? How hard is it to do? N log n-ish, right? It's actually, yeah, it depends on the number of machines and jobs, but probably you don't have a lot of machines, so it's n log m. If you use a priority queue, it should be n log n, as long as you don't care about m. But they found in 1966 that the greedy approximation is a 2 approximation. So it's at most a factor of 2 from the other. How do we know? Well, how can we characterize? We don't know what the heck the optimal is, right? Well, we don't know what it is, but we can do 2 things. First of all, we know that that optimal makespan is bigger than the largest job. Worst case scenario, right? One machine has to take the largest job. So, right, that's the best you can do with that one. Just give it to that machine and don't do anything else on that machine. So at least you have to do that, right? The other one is at least you have to do the average, right? So if you could do perfectly and assign every balance the jobs perfectly, you would still, right? The optimum has to be at least the average. Does that make sense? And one of them will be bigger, right, in any given problem. But so the greedy algorithm is a 2 approximation. How do we show that? Well, you have one machine that ended up with the highest one, right? Let's call that one I. And so that has a load of Li, right? And let J to be the smallest job scheduled on that machine. Right? When when you assign that job to that machine, right? It had the smallest possible load. The smallest load out of all the other machines. Right? So it was less than all the other ones at the time, and of course, less than everybody else. And so the worst that you could do, right, is, right, to assign the longest one to that one. That would have slightly less than the average, right? So the worst that you can be off is the longest. So if we make this assignment, right, Li minus Tj is less than Lk for all the machines. If I add up over k and divide, I get it is less than 1 over m, so it's less than the average. And I know that the optimum is at least the average, so it's going to be less than that. So the extra that I added, right, is less than the optimum. And so at most, I will add almost twice. Does that idea make sense? Either in math or in words. So without knowing the optimum, we know that at most we added 2, right? Is the analysis tight? Yes, except this, maybe off by 1, I think. So it is reasonably tight. Now, we can do better, right? What's my problem? Well, the last one that I add, right, could unbalance my thing. So what can I do? Well, sort them by longest time first, so that the one that I add at the end, right, is as small as possible. And so if there are more than m jobs, you get 3/2 approximation. So as long as you don't have too few jobs, you get within 3/2 of the optimal. Isn't this cool? We'll never know what the optimal is, but we can find something within 3/2 of the optimal. And that's an NP-complete problem, right? So what does that mean? I can transform anything else into this one, right? So if I really have to, right, I can do those kinds of things. Is this tight? Not really. So somebody else proved that it's actually 4/3 approximation. And that's about the best we can do. Another problem is the center selection problem. Given a set of n sites, S1 to Sn, and an integer k greater than 0, find a set of k centers so that the maximum distance from a site to the nearest center is minimized. Have any of you been doing machine learning stuff? Have you taken any of those classes? What is this guy in machine learning? What is this kind of stuff? K-means, right? K-means-ish. It's clustering. When you are doing unsupervised learning, right, this is something that many times you want to do, just finding the clusters that will, in this case, slightly different, depends on what you are doing, right? Here what you are trying to minimize is the distance. When you do k-means and k-methods algorithms, you have others, maybe some other things that you're optimizing, but it's very similar to k-means. Or actually, we'll end up doing K methoid. So how can I do that? Can I do that in polynomial time? Well, can I do that in, how can I brute force this? Can I even think about brute forcing this?
Try a circle and no, that's too much.
I have a bunch of circles, right? But what are all the positions, right? Imagine that I'm doing, in this case, I'm doing 4 centers, right? So I'm doing 4 blue things. What are all the possibilities for each one of them? It's the 2D plane, right? So how many possibilities do I have? Infinity squared, right? It's infinity on both sides, right? So you can't, right? I mean, that's too many. We could use K methods rather than K means. Well, what if I choose only from the elements, right? So only from the places that you gave me. And that would get it into some form of exponential thing, right? I have subsets of size this, right? So it's factorial-ish. It's combinations or permutations or one of those things, right? Doesn't that suck? Yes. Well, some notation. We are going to call this xy, distance between size x and y. And we're going to call distance of SIC, where C is a set of centers. The minimum distance to the center, so distance from SI to the closest center. And RC is the smallest covering radius. It is the maximum distance over all the sides of the sides that fall within me. If I'm a center, right, is the biggest one, the biggest distance of the sides that fall within the center. Does that make sense? So what I'm trying to do is find a set of centers C that minimizes R of C subject to size of C equals A. We will use, this is the standard definition of distance in math. You need 3 properties of a function to make it a distance function. One, the distance from something to itself is 0. Second, distance of xy is the same as distance of yx. So it's symmetric, and it also satisfies the triangle inequality. Euclidean distance on a plane satisfies this, but it can be other kinds of distance, right? Makes sense? So if we were just searching every possible point, we could get infinity. What else can we do? Well, let's be greedy. What do I do? Well, one possible greedy way would be put the first center at the best possible location for a single center, right? And then keep adding centers so that you keep doing that in a way, right? To reduce its covering radius by as much as possible. So what do we do? How can I find the greedy center? That's just the center of gravity, yes? Yeah, that's just, right? the average x and y. Thank you. Cool. Right, the center of gravity of those things. And then I would start, right, putting on different places so as to get the other places, right? What is the problem with this algorithm? Please establish. Well, if you have something, right, and it's very easy to see, it's arbitrarily bad, it's not good at all. If you had two places, right? If you had your data distributed on two sides and your k is 2, the first one will be in the middle, and the second one will be, right, in the center-ish, which would make it sort of suck. The first one would suck. The second one would be okay, right? But the first one would suck. Does that make sense? And so by using this, you can actually see, okay, if you have just two dots, that's it, right? Then you would have, you could, and k is 2, you could have your optimal is 0, just put one on each side, and this one will give you something a lot bigger. There is a better one. Start picking, right? Pick one at random and then repeatedly choose the next center to be the one furthest from any existing center. Actually, it's not. Yeah.
How does that work exactly? Like, I'm imagining the last graph, you just randomly put down.
The first one, here you're choosing sides, right? So you choose a point. So you choose this one. And now you're going to choose the point that's further from that one.
Okay.
That's going to be your next center. So you're going to choose maybe somewhere in here.
Okay, I was thinking when it said the next one that's farthest away, I thought it meant the next point as in not the site, but the next distance point.
No, these are sides. These are sides. Yes. And so upon termination, right, all centers are at least RC apart, at least the optimum apart. And the one that we have, right, this algorithm gives us one that is within 2 of the optimum. Imagine that this were my true optimal centers, right? And I chose 4 sites. How bad could I be, right? How far off could I be? At most, I could be
Radius of a circle.
2 of this, right? So at worst, I could be twice as far as I would need to be. Instead of being, right, imagine that I'm at this point, instead of calculating the distance to the center, I'll calculate the distance to one of the other points, right? But that other point can be at most twice that distance, because that other point can only be one distance away from the true center, from the optimal center. So worst case scenario, I am twice as bad if we are only considering distance. Isn't this cool? Can we do better? Maybe. There is actually tons of algorithms for this particular problem, because this is clustering, that look at it in different ways. But we know for certain definitions, right? And there is different ways to define how good your clustering is. Not just the max distance, but for this one we have an approximation. We know, unfortunately, we cannot do better than 2. Because if there is, we would be able to solve the dominating set problem in polynomial time. What the heck was the dominating set problem? The fountain of all knowledge tells us. Is a set of vertices, subset of vertices of a graph, such that every vertex not in there is adjacent to at least one member of the graph. And that is NP complete. And we could solve it, we could transform it into a centered selection with these distances, and so that would preclude us from guaranteeing more than 2, closer than 2. So life sucks sometimes. Vertex cover. You remember vertex covers? No.
Oh yeah.
Yeah? Good. It is similar, right? It's a set such that each edge in E has at least one end in S, right? So a set of vertices in a graph, right? Now, the weighted vertex cover is given a weight on the vertices, find a vertex cover of minimum weight. The algorithm is based on what they call the pricing method. Each edge, given that each edge must be covered by some vertex, we could say that each edge ij pays a price to use both vertex I and j. We have a fairness assumption, which would say the sum of all the edges incident in here would be less than the weight. if that is okay, if you have a vertex cover and a set of fair prices, you would have this inequality, right? Summation of the price for each edge is going to be less than or equal to the summation of this not equal. I is in S, which is my set of, yeah, the sum of all the edges that are incident on this guy. This may allow for it to be counted twice. That's why it's less than or equal rather than less than. And it is equal than the set of all weights. Does that make sense? This would allow me to count it twice on some of the vertices and not to count it for one vertex and not to the other, basically. So here's my algorithm. Start my vertex cover, right? Start by S to be the empty set. Assign the price 0 to each edge, and then go finding edges. So while there is an edge that is not tight, so that is not paying, that it has more to pay, right? Then find or assign, get that edge, and increase it until it's all tight, till it's tight, and add. The S is going to be the set of all tight nodes. So imagine that we have this. Let's assign, which one did I assign? This guy. Let's select this guy to be there, right? So how much can I assign to it? How much can I make it pay? At most 3, because that would make it tight on this side, right? That would mean if I make it more than 3, then it would break the rule that the sum of the weights or the sum of the prices for the edges is less than or equal than the weight. Does that make sense? So now B is tight. Let's assume that I choose this guy, right, or that edge, sorry, the AD edge. How much can I pay to make it tight? At most 1, because now A only has 1 extra. It has 4 total weight, but BA, sorry, is paying 3. So at most I can do 1, right? That would be this. That would be figure C, and then I can choose CD, and I can pay at most 2 to make it tight.
So from B to C, we can pay any more.
Well, you don't need to. Oh, yeah, you can't, right? This one is tight, so you can't choose it. And this one is tight, so you can't choose it. Once you chose this one. The algorithm just says pick one at random. The pricing method is a 2 approximation for the weighted vertex cover. So at most, I'm doing twice what I should do. How can how can I prove that? Well, first of all, the algorithm terminates, right? Because at least one node becomes typed. So at most, I go through n edges and I'm done. So S is going to be the set of all type nodes upon termination. It is a vertex cover because if there is an edge ij that is uncovered, neither I nor j is typed, so I would not terminate. Right? And by definition, if they're not covered, then the other guys are not, the vertices are not typed. And my inequality, right, basically what I could be doing is counting each edge twice. And so at most I am at twice. The words that I could do is if I'm giving to each edge twice the weight. And so I can do something, right? A two approximation. It's not that bad. Could be worse, right? There is another way which introduces an interesting set of algorithms that we are not going to cover, but which is linear programming. Maybe we should, but I'm gonna cheat and not cover it. So weighted vertex cover, right, is what we just talked about. Find the minimum weight subset of vertices. Every edge is incident to at least one vertex in S. There is something called linear programming, for which we have a really nice algorithm that solves it. However, that requires floating point weights. Integer linear programming says, okay, you do the same thing, but your coefficients have to be integers, and that is not solvable anymore. That's NP complete. However, we can cheat. It's called linear programming because you have a bunch of linear constraints.
What's a linear constraint?
You have your variables in linear combinations. Basically, they are not squared, they are not absoluted, right? You have a linear combination of variables and a constant. So your constraints have stuff like xi, but not xi squared, or absolute value of xi, or something like that. So you end up with your variables. You're going to have one per vertex, and it's going to be 0 if the vertex is not in the vertex cover, and 1 if it is. Your objective function, which is what you're trying to minimize, is this. And you also have this other linear constraint, right? So this is what your linear programming problem looks like. This is what you're trying to minimize, subject to xi plus xj greater than or equal to 1 for all I and j in E, and xi is either 0 or 1. And this is what makes it integer linear programming rather than linear programming. if you find a solution to this, then you found a minimum vertex cover. This actually proves that integer programming is an NP-hard search problem, but the cheating way is solve the linear programming, which is solvable in polynomial time, using the simplex algorithm or some of the other algorithms.
What do they mean by in practice as opposed to polytime?
It works.
Like they use it in business situations?
Simplex, yes,
outside of
exactly.
the
And
research environment?
yes, in fact, linear programming is used all over. It is the standard maybe it's not anymore, but it was the standard optimization thing before fast computers. You can do it manually. They used to torture people in undergrad degrees in several engineering disciplines by making them solve this manually. I've never, I'm not old enough to have been tortured by doing it manually, but I was tortured at implementing it. See, what is the let's see, seed implementation, seed polynomial efficiency, there it is. Okay. They thought that it was polynomial at the time, but then it was proven later that it's not. But for some reason, it's the one that they teach you. Or at least that's what they called it when they taught it to me a long time ago. But then they found other algorithms that are polynomial. The simplex solved a bunch of fairly useful problems. Took a while for them to show that it wasn't. And it didn't solve every problem. So linear programming is super used. It's used all over for optimization. I'm assuming that now we tend to, they probably still look at linear programming, but now you use integer-ish linear programming because you have computers. So you use either, if you can do it as a linear programming problem, then that's a great thing because that's solvable. You just put a matrix onto a computer, press enter, and it wouldn't surprise me if Excel can solve linear programming now. Yeah. Excel solver has linear programming. So, right, if you can put it as a linear programming, then you got it. However, this is integer linear programming, which is NP-hard. In 2D, this is kind of what linear programming looks like, and simplex would tell you that you find this guy or something like that. The relaxation would be let's do greater than or equal to 0 instead of 0 or 1. And then in the end, what this allows me is say, oh, you do half of this vertex and half of this other vertex, which is done. So in the end, I need to make them all ones, right? If it was half, you make it one. And so it's not optimal, but it is an approximation with at most twice the optimal. Which is cool. We have, and would be interesting to go look at that, but I don't think I'm gonna. Somebody proved, right, that the most you can do is 1.3606. But we haven't we haven't reached that constant. So the best you could do, unless p is equal to np, is 1.36. But we don't have algorithms that do it. Let me mention, I'm gonna skip generalized load balancing and go to the knapsack because we talked about it. And again, right, the fractional knapsack problem is super easy. The integer one is not, right? But we do have an 1 plus epsilon approximation algorithm for any constant. If you remember, what was the knapsack problem? You have a knapsack of limited weight. You're trying to fill up with as much money as you can, as much value as you can, subject to the weight constraint, right? If you have fractional, right, so if you can just choose, if you had like gold, silver, and platinum or something like that, then you would just, if it's dust or liquid, then you could just pour all the platinum, which is probably the most expensive, then fill up with as much gold as you can. But if you have them in ingots, right, then it may be worth to you to put 2 silver ingots because they weigh less than a gold ingot or something like that, right? And so you may have space for some silver or something like that in your knapsack. If you remember, we looked at it also in the we saw a dynamic programming algorithm for it, but it fills up the table on all the possible weights. So if your weight is big, then you end up with O and W. So if that W is big, you end up with a very inefficient algorithm. If the weights are small, then it would be polynomial-ish in input size, right? So what we can do is cheat and divide our weights, or the other way around, divide our values so that we end up with small, I think this figure is wrong, because it is the weight, not the values. So divide our weights and the values so that we end up with smaller weights.
On that one, it looks like there's smaller values with the same.
Well, you need to divide both of them because it's value per weight. No, it doesn't matter. Yeah, but it's weights, not values. Yeah, they messed up the figure.
Okay.
This should be weights. These are values. Yeah, no, it's not. It's not value, it's weight. What I need to. Because here I'm doing weights. Oh, no. It is values. It is values. Sorry. It's not on the weight, it's on the value. What's going to be on my table, right? Is. Sorry. What's going to be on my table is weights. So it doesn't matter what the values are, it matters what the weights are. This slide is wrong. But that would allow me to solve it within whatever constraint I want, which is really cool. Depending on my epsilon. So depending on how much do I want to compress that thing. Isn't this cool? Cool. That's all we talked about, approximation algorithms, and we're going to skip the one in the middle. We're going to skip the generalized load balancing algorithm. I promise you I will not ask you on the test. Any questions? No? Cool. Then I'll see you guys on Wednesday.